Welcome to this explainer. Right now, in whatever room you're sitting in, you are completely surrounded by an invisible, chaotic architecture. It's true. Every single time you speak, or tap your desk, or play a song, these invisible waves of acoustic energy just erupt outward. They're bouncing off your walls, the ceiling, the floor, colliding and crossing over one another in this incredibly dense web of reflections. Now, obviously, we can't see this complex topography, but our ears, they feel its effects every single day. So today, we're going to explore the fascinating, highly precise science of exactly how we measure and ultimately tame this invisible terrain.
But to really appreciate where we are today, we kind of have to look at how this whole thing started. Right around the turn of the 20th century, a Harvard physics professor named Wallace Clement Sabine essentially birthed the entire field of architectural acoustics. But get this, his tools for doing so were incredibly primitive. He literally used organ pipes to generate sound, his own ears and a stopwatch to measure the reverberation decay, and a bunch of seat cushions he borrowed from a local theater to absorb it. I mean, it was absolutely groundbreaking work at the time, but he was essentially trying to map a complex, multidimensional room completely blindfolded.
So that brings us to the core problem we still face today. Bad acoustics completely ruin good sound. And whether you're designing a world-class recording studio, a massive concert auditorium, or honestly just trying to get your home theater to sound right, you run into one fundamental truth. You cannot fix what you cannot measure. So how do we accurately map an environment that we literally cannot see? Well, we need a tool that can essentially see sound in 3 dimensions.
For the longest time, people just relied on a basic mobile SPL or sound pressure level meter. You can think of an SPL meter kind of like a basic thermometer. It tells you the total energy or the overall temperature at one single point in the room. But here's the catch. It is time blind, frequency blind, and direction blind. It absolutely cannot distinguish between the pure, pristine sound coming directly out of a speaker and the messy, chaotic reflections bouncing off the back wall. We desperately needed something better. Enter the Advanced Acoustic Analyzer. If the SPL meter is just a basic thermometer, this advanced analyzer is a clinical, 3D radar system that maps the exact architecture of the room. Historically, acousticians tried to measure rooms by popping balloons or firing starter pistols, basically creating what's called an impulse. But impulses have a really poor signal-to-noise ratio. A gunshot's tail easily gets lost in the background hum of, say, an air conditioner. They also trigger massive amounts of distortion. What we really needed was a hero tool. And that tool turned out to be swept sine transmission. By smoothly injecting this sustained, controlled energy over time, it fundamentally solved the noise and distortion problems that plagued all those earlier acousticians.
Section 1. The swept sine solution, revolutionizing acoustics.
So the crucial point to understand here is that a swept sine wave isn't just a static, boring single tone. You really want to think of it as a dynamic, probing radar. A loudspeaker system systematically and continuously sweeps through frequencies, moving from the deep, rumbling lows all the way up to the sparkling highs. And by doing this over a duration of time, rather than just one instantaneous burst, we inject a massive amount of acoustic energy into the room. This cuts right through any ambient background noise and allows us to map the room's geometry with unbelievable precision.
Now, this dynamic probe enables an absolutely genius invention by Richard Heiser called time delay spectrometry, or TDS. It essentially works like a perfectly synchronized dance. First, you send out that swept sine signal. But, sound is actually pretty slow. It travels through the air at a leisurely 1,130 feet per second. So step 2 introduces a calculated time delay to account for that. Step 3 is where the magic happens. The receiver's sweep is offset by that exact delay time. This means the receiver is perfectly tuned to catch a specific reflection arriving at that exact microsecond, while actively rejecting all the other ambient room noise and later echoes.
Section 2. Schroeder frequency, crossing the threshold.
There's a literal border crossing in the physics of whatever room you are in right now, known as the Schroeder frequency. This usually sits around 300 Hz in smaller rooms, and it literally divides the room's behavior into 2. Below 300 Hz, the room acts a lot like a series of jagged, isolated resonating pipes. You get these deep nulls where the bass just completely disappears, and sharp peaks where it suddenly booms. But as we cross that Schroeder frequency threshold into the higher ranges, the acoustic environment completely transitions. The modal density increases exponentially, and the sound waves start overlapping into this smooth, statistical continuum of energy.
Our swept sine probe captures all of this chaotic data beautifully. But here's the thing, raw sine data of a room looks like a disastrous seismograph with crazy 35 decibel swings all over the place. Our human ears naturally integrate narrow spectral deviations, kind of like squinting slightly so you can see the big picture of a painting. So, to account for that, we process this raw data into fractional octave bins, typically using 1/3 octave smoothing. By diminishing those microscopic, sharp anomalies, the data we analyze perfectly matches the psychoacoustic correlation of how our human brains actually perceive tonal balance.
Section 3. Time delay spectrometry. Isolating anomalies.
By utilizing these delayed time slices, time delay spectrometry allows us to separate two entirely different physical problems in a room. On one hand, we have model resonances. These are driven by the physical dimensions of the room itself. They maintain their peak shape over time and ring out like a bell long after the original sound stops. On the other hand, we have boundary interference. This is a non-resonant geometric echo caused by sound bouncing off a hard nearby surface, like a wall or a mixing desk. It doesn't ring at all, it just interferes geometrically. Now, when those static boundary reflections combine with the direct sound coming from your speaker, they create something truly terrifying for audio engineers: comb filter distortion. It causes incredibly destructive phase interference. For instance, if a reflection arrives just one single millisecond after the direct sound, it creates a massive energy null at exactly 500 Hz and completely destroys the frequency response every 1000 Hz after that. If left untreated, this invisible comb filtering can completely ruin speech intelligibility and musical timbre. Honestly, this is exactly why you sometimes have to turn on subtitles just to understand the dialogue in a poorly designed home theater. Section 4. Sculpting the acoustic field, fixing the room.
So how do we actually use all this data to fix these anomalies? We use an energy time curve to design what's known as a reflection-free zone. Our baseline is our temporal anchor at time 0, that's the pure direct signal from the speaker. What we want to do is use acoustic panels and diffusers to carve out an initial signal delay gap. This is basically a valley of 10 to 20 milliseconds of pure acoustic silence before any room reflections hit our ears. Any early reflection that arrives within the first 50 milliseconds and is too loud will completely destroy our brain's ability to perceive a perfect stereo image.
Please take just a second to really absorb this concept, because it changes everything about how we understand room design. Acoustic mastery is not achieved by treating volume. It is achieved by sculpting time. We aren't just turning down the overall volume of a room, we are clinically and purposefully managing the exact arrival time of energy to preserve the clarity of the source material.
Bringing it all together, by using a swept sine probe, we have essentially upgraded from that simple one-dimensional thermometer to a unified 3D map of the invisible world. We can now map frequency to visualize that Schroeder transition, energy to reveal phase-canceling boundary interference, and time to show us exactly where we need to carve out our initial signal delay gap. It's truly a game changer.
It's just incredible to think that a little over a century ago, we were literally using stopwatch clicks and theater seat cushions to try to understand our environment. Today, we map time, energy, and frequency in 3 full dimensions. But you know what? It really leaves you wondering. If we can now perfectly map and sculpt the invisible architecture of sound, what other invisible forces around us are just waiting for the right probe to be discovered? Thank you so much for exploring the swept sine methodology with us on this explainer. Keep wondering and keep looking for the invisible.